Hello and welcome to the lecture number 16 of Physics 401A. In this lecture, we start discussing on the theme small oscillations. In classical mechanics, as we have already discussed, that two central potentials are of specific importance. One is 1 by r type of potential, another is r square potential. Because Bertrand's theorem says that only these two central potentials lead to always closed orbits whenever we talk about the finite motions under these potentials. Okay. 1 by r potential is also important because in nature we can see them, to a large extent of spaces. For example, gravitational interaction, Coulombic interaction. Gravitational interaction is always attractive in nature, but Coulombic interaction can be both attractive and repulsive. Okay. On the other hand, r square potential is a potential which we can see for the motion of the simple harmonic oscillators. Okay. And this is the motion which is the result or the outcome of a very small perturbation about a position of stable equilibrium. Now, it is true that we all know what stable equilibrium is. Basically, you all know from Newtonian framework that stable equilibrium, so for example, a position of equilibrium is such a position where the net force acting on the system vanishes and the potential energy has an extremum value. And stable equilibrium position is nothing but the position where the potential has its minimum value, right? So here in this case, we will try to define the same concept or same notion of stable equilibrium in a slightly different way. Okay. So for this, we need to define another concept which is known as the natural systems. Okay. So in the current context, whenever we talk about the equilibrium, we talk the equilibrium of a natural system. So the natural systems are the systems we see usually. Okay. In the physical examples for the physical systems, most of the cases they are natural systems. Very small number of systems are there which do not obey natural systems. Which do not obey the rules of the natural systems. So what are the characteristics of a natural system? First is that the position vector can be denoted by the generalized coordinates. Okay. Or rather, first I am just saying that only in terms of space coordinates. Okay. Whether they are generalized or not, I am coming to that. Okay. So just space coordinates q1, q2 up to qn. Okay. All the applied forces are conservative in nature. That does not say that there should not be any constraint force which is dissipative in nature. It is just saying that all the applied forces or the body forces, okay, which is applied on the system are conservative in nature. Let's say the gravity, okay, this type of thing. All the constraints will be holonomic, and that's why the first condition can now be said in terms of the generalized coordinates. So if you have all the constraints which are holonomic in nature, then effectively you can describe the system by a set of generalized coordinates which are if n in number, then n will denote the effective degrees of freedom of the system. Okay. Finally, kinetic energy should be a quadratic function of the velocities or the generalized velocities. Okay, that we already have seen that, and a generalized definition, okay, for the Lagrangian of such a natural system is of course half summation over I and j, both are running from 1 to n, where small n is the number of effective degrees of freedom. So the total number of generalized coordinates and velocities, of course, summation over aij qi dot qj dot, okay, minus uq, where aij, they are in general the function of the generalized coordinates. That means only q's. Okay. And when I write just u as a function of q, u is the potential part, you all understand, this is the generalized expression of kinetic energy, then this q means that it can contain any, I mean actually any number of queues like qy's. For example, q1, q2, q3, okay, up to qn. So this is a general, this is just denoting a general dependence on the queues. Okay. Now let us assume a position r0, okay, which is a function of q01, q02 up to q0n, where this is a specified position. That means this is a constant position. Okay, this is a constant vector, and all the q01, q02, they are also just the numbers, they are no longer variables. Okay, at which qy dots is equal to 0 if qy dot is equal to 0 at time is equal to 0. So the meaning of this is that now if in the system moves, then if we find somehow a position of the, I mean position in the field of motion of the system such that the position will retain zero generalized velocity. You just remember these things. So this is a generalized velocity, the ith component of generalized velocity. Okay, I should not say ith component because I cannot always write a generalized velocity vector for like that, but it's just one of the generalized velocities. So ith generalized velocity, okay, is 0 for all I and for all t if we pre-assigned that its initial generalized velocity is 0. Okay, if we have this condition, then r0 is called a position of equilibrium. So here you remember that we are defining the position of equilibrium without using the concept of force and potential energy till now. We are only using the position and the, I mean condition or constraints or restrictions on position and the generalized coordinates and the generalized velocities. Okay, so this is a kinematic definition of the position of equilibrium. That initial generalized velocity I vanish, okay, somehow I vanish. At all the later instants, the generalized velocity will remain vanished. Okay. Now recall the form of Euler-Lagrange equation as ddt of del t del q k dot minus del t del q k is equal to minus del u del q k. So this is not the final form of Euler-Lagrange equation. This is just the penultimate form of Euler-Lagrange equation, which was just obtained just before writing the total thing in terms of Lagrangians. Okay, but this was also equally true. Okay, if we write this equation, then we can evaluate the first term del t del q k dot, and with the generalized expression of t, which is given over here, this one. Okay, we can say that del t del q k dot will be del q k dot over half summation over I and j aij qy dot qj dot. Now that will be simply equal to summation over I a ki qy dot. Okay. Again, if you now, okay, just to tell you, now ddt of this thing will be, of course, gives you something like a summation over I a ki, okay, qy double dot plus summation over I ddt of a ki qy dot. Okay, so you will have two terms. Now another term will be there del t del qk, which will be nothing but half of del aij by del qk, because aij is the function of coordinate. So any partial differentiation with respect to the qk generalized coordinate will act only on this part, because the rest is just the generalized velocity. Okay, so this will be half del aij del qk qj dot qk dot. Okay, Now we know that for the position R0, del T del Q K dot is equal to 0, and also ddt of del T del Q K dot is also 0. That is 0 because we said that if the initial velocity is 0, okay, then the final velocities will also be 0. Okay, and that is the definition of R0, that it's so I mean actually here we are assuming the case where initial velocity is made to be 0. Okay, then it's so qi dot any time, I mean every term. So basically if you do ddt of del t del qk dot, you will have ddt of the whole thing. So this will give two terms, basically ddt of the whole this term, and one term will be just including qi dot at uh, r is equal to r0, which will vanish. Another term will involve the ddt of qy dot, and this is also 0 because the velocity does not change. If it is 0 at time instant 0, I mean time instant t is equal to 0, it will remain 0. Okay, so that's why under the condition that the initial velocities are assigned to be 0, okay, initial generalized velocities are assigned to be 0 at r0, finally you have this term will be equal to 0. Okay, just check this. Okay, this is a small but good exercise. Okay, and this is also 0 for the simple case that this is evaluated at r is equal to r0, and again qj dot qk dot at 0 at r is equal to r0 at all instant. So finally I can say that if r is equal to r0 is the position of equilibrium, then for that both of them will vanish. Okay, and then in order that this equation be true, minus del u del q k should also vanish, and that finally leads us to the well-known definition of the position of equilibrium, that is you should have an extremum value at the position of equilibrium. Okay, and that is true for all k. Okay, and so of course you can directly start from 2 without using all these definitions and all these explanations, but then the thing is that you have to start from the generalized force or the concept of potential. Here we are just starting from the very general kinematic definition, and this type of definition is actually necessary when we will do nonlinear dynamics and we will start finding the fixed points in phase space. Then this type of definition will come into play. Okay. Now a position of equilibrium is defined, but now we have to classify them. So they are stable if u has a minimum, local minimum actually. So the first order partial differentiation will vanish. Okay, but the second order one will always be positive. That is the rule for, condition for minimum. And if it is unstable, then u actually is a maximum. Okay, at r is equal to r0. So del 2u del q2 will be a negative quantity. Okay, but in both cases the first order derivatives with respect to qk's will be vanished. Okay, so here we study the motion of a particle which is disturbed by only a very small quantity. That means what we say in physics, the first order perturbation, very weak, with respect to a position of stable equilibrium. Okay, so we now consider that R0 is a point of stable equilibrium. Now for simplicity we take the one-dimensional case, and we start by a system with only 1 degrees of freedom. That is basically the synonymous of saying this is a one-dimensional case. Again, that means that only one couple of q and q dot. Q0 will be our equilibrium position, of course stable equilibrium, because we are interested in that now. So let us now perturb the system by moving it slightly from Q0 to Q0 plus delta Q. So that will be just from Q0 to Q0 plus delta Q, or it will be just by moving it from Q0 by a distance delta Q. Okay. Then we write by Taylor expansion U of Q0 plus delta Q is equal to U of Q0 plus del U del Q evaluated at Q0 times delta Q plus half del U del 2U del Q2 again evaluated at Q0 times delta Q square. Okay. So delta Q is nothing but instantaneous Q minus Q0. Okay. So then we can say that as U is a minimum, U has a minimum at Q0, then we can again say that this is a positive quantity and this is 0, right? So this vanishes and this is a positive quantity. Okay. Now we can easily say that we define, without losing any generality, U at Q0 is the minimum value of U. So we can define that as the reference value of the measuring the potential, as we in general do, and we can make it by choice 0. So then we get rid of this quantity. Okay, and then finally we can say that the resultant U which is acting over here is nothing but half this positive quantity times delta Q square. Once again, you can see that this is an expansion, series expansion, which goes up to infinity. So we are simply not considering the higher order terms and we stop at here because delta Q is a very small quantity. Okay, so only it has second order smallness. We could have actually just taken up to first order, but as the first order term vanishes due to the equilibrium condition, we have to take, this is the first non-zero contribution, we have to take that. So the first non-zero contribution is of second order of smallness, right? We are just neglecting any higher order terms of delta Q here for our simplicity. Okay. Now, of course, if delta Q itself is not very small, then there can be instances where you can actually take the higher order terms. Okay, maybe in some later lecture we will discuss about that, and you can actually see that, not maybe, but when we will talk about perturbation theory and nonlinear oscillators, then we will see this type of thing will then be considered. Okay, we are now just called delta Q as X, so that it is, looking much more compact, and the resultant potential is half kx square. So you see we have again a potential which is like a quadratic potential, half kx square. Okay, and then you can easily understand that so in one-dimensional case, this is not a, this is trivially a central potential, right? Because only one distance is there. So let's say in a higher dimensional case, this is a central potential if the total potential has a form of half kx square plus half ky square plus half kz square. Then you can say that the total potential contribution will be half k of r square, right? Okay. And that is then actually we can talk about a central potential. Here for one-dimensional case, central potential and normal potential, they are just synonymous. Okay. Now, if we are making our Lagrangian in such a fashion that terms with second order smallness will be retained at maximum, just making compatible with the order of smallness of the potential contribution, we can say that T, which is half A of Q dot square, will simply be equal to half A of Q0. That means A evaluated at Q is equal to Q0. Okay, that means I am just taking their zeroth order contribution times X dot square. Okay, Now you can easily ask me that, okay, so x dot and delta, so q dot and delta q dot, they are the same thing, so that's why q dot and x dot, they are the same thing. Okay, that you understand. But the question is, what is the guarantee that if q is small, x is also small? That is the thing you have to understand, that here we are just talking of a perturbation making small displacements, very small displacements. Now if you don't have a viscosity or any resistance or any friction, any other resistive force in the medium, then it is a very intuitive. So it's from a physicist's point of view, it's intuitive that you only need a very small velocity involved in the whole motion so that the displacement is small. Okay, unless there is a very high impulse, external impulse, which we are not considering here. So that's why if the q's are of first order of smallness, here in this case the q dots will also be, or actually x dots will also be, the first order of smallness. And that's why we just take the quantities of half a q0, which is a constant quantity, so it's a zeroth order quantity, times x dot square. Okay, I call aq0 as m, and you all know that this is nothing but the equivalent of the mass of the system. And then the resulting Lagrangian becomes half mx dot square minus half kx square. Okay, that you can all write. Okay. Now, of course, you can say, sir, we all know how to write the Lagrangian right from the beginning. Then why are you doing all these things? That's because how to develop formally, starting from the kinematic definition of equilibrium, it is good to know how we write finally the Lagrangian of such a system. And then Euler-Lagrange equation gives us mx double dot plus kx is equal to 0. So mx double dot will be proportional to minus x, simply because that mx double dot will be minus kx and k is greater than 0, because remember k is nothing but this del 2u del q2 evaluated at q0, and this is a positive quantity for the minimization condition of u. Okay, so finally we know that we have mx double dot plus k, which is a positive quantity, times x is equal to 0, and this k now can be written as m times omega square. I can write that k will be proportional to another positive quantity, which is the mass, and I just say that the ratio of the two will be omega square. Then I can easily write this. So then I have this equation finally, x double dot plus omega square x is equal to 0. So look, actually all of you know how to solve the equation, how to write the equation for a simple harmonic oscillator, how to solve that. Okay, but here in this course I am trying to give you an alternative point of view just by using Lagrangian formulation and kinematic definitions, how far you can reconstruct all these things which you have already seen in Newtonian mechanics. That's exactly the thing. Okay, otherwise doing just solving these, writing these equations, okay, they are all a repetition. Okay, it is the approach which is new. Okay, now we all know, but somehow we have to solve this, as we have already solved, because finally as we claimed that our final target is to solve for x as a function of t to designate the state of the system. That is the objective. And we all know that cos omega t and sin omega t are two independent solutions for xt. In some books you can see that the solution word is not there, so they just say that integrals. So for algebraic equation they use the term solution, and for differential equation they use the term integral. That is not the integral of motion, that is the integral of the equation here. Integral of motion is a constant of motion independent of time. Okay, but integral of equation is a solution of differential equation. Okay, so then you can easily write that xt will be equal to c1 cos omega t plus c2 sin omega t, and then by using high school algebra you can see this is equivalent to A cos omega t plus alpha, okay, where I have introduced A and alpha, okay, both are constant such that A is equal to root over C1 square plus C2 square and tan alpha is equal to minus C2 by C1. These two results I suggest you to reproduce at home, okay. Now from the above analysis, this is clear that a system performs harmonic oscillations when gets a very small perturbation with respect to its position of stable equilibrium. Okay, so we knew what the equation of harmonic oscillator is. Now we saw basically that if a particle is perturbed by a very small amount, okay, and a very small amount of velocity is also involved, then the particle will perform simple harmonic oscillation. Okay. My question is, what happens for weak perturbation about a position of unstable equilibrium? Can you put some light on that? Just think. Okay. Now we try to define various parts of the solution. One is, so xt can be written as A times cos omega t plus alpha. A is the amplitude of the oscillation, that is the maximum displacement possible. Omega is the angular frequency, or simply roughly called frequency in physics sometimes. Alpha is the initial phase, so that means that at t is equal to 0, how to designate x, how to measure x. At t is equal to 0, okay, then x will be equal to A cos alpha, right? One very important thing to remember, that frequency is something which is determined by the properties of the system and cannot be altered just by changing the conditions of motion. So frequency, that omega, is a source property and it's independent of the initial condition of motion. Okay, so if the source is modified, then only we can think of altering or modifying the frequency. We will actually see that instance when we will talk about parametric instability or parametric resonance. Okay. Now, from the equation of dynamics, you know that mx double dot plus kx is equal to 0. It simply says that E half mx dot square plus half kx dot square is equal to constant. Okay. Then we just write this solution x is equal to A cos omega t plus alpha. We can easily say that x dot is equal to minus A sin omega t plus alpha times omega. There will be an omega. Okay. And finally E will be simply equal to half m. So then you just substitute the values of x dot and x here in the expression of E, and you will have half ma square omega square sin square omega t plus alpha plus half k square cos square omega t plus alpha. Again, k is m omega square by definition. So finally this will give the same thing twice, and added up it will simply, I mean not same thing twice, but it will give you the half m a square omega square sin square omega t plus alpha, and this will give you half m omega square a square cos square omega t plus alpha. So being added, they will give you half m omega square is a square to be the total mechanical energy of the system. So remember now, this total mechanical energy basically depends on m omega square, so it depends on k, that is the stiffness constant. If you just remember now, if you just now try to model or try to put an analogy between a simple harmonic, general simple harmonic motion and the motion of a spring, you can really relate that k to the stiffness constant of the spring. So E is proportional to that stiffness constant of an equivalent string here. Here we are not talking about a spring, but you see that there is an invisible spring which basically causes this simple harmonic oscillation. Okay. Again, E is proportional to A square. Okay. Now sometimes here we have just talked about this trigonometric solution, if you remember here, but sometimes it is also useful. Now we will see in some in a while that it is useful to introduce complex notation. That means instead of the trigonometric notation, we just use e to the power I theta, which is equal to cos theta plus I sin theta. And then if we need to put, need to finally extract the solution, we will extract the solution just by capturing its real part or imaginary part according to the condition necessary. Okay. So then basically x is equal to a cos omega t plus alpha can be written as real of a times e to the power I omega t plus alpha. Here the cos part is there, so I can just take the real of this e to the power I omega t plus alpha, so that I have the cos term finally. So a is a constant itself, okay, but a is a complex number. Okay, so if a is a complex number, then just a minute, not this a. This a is a real quantity, so I can just easily write this in the following way. This a is a real quantity because this x is real total. Okay, so if I just write this real of this quantity, then I can easily write a this quantity as a e times e to the power I omega t times e to the power I alpha, and then a times small a times e to the power I alpha. I can define that as a complex constant quantity, which is the complex amplitude. Okay, and if we can easily use this complex number, which is a times capital A times e to the power I omega t, and just by extracting its real part, we finally get the solution for x. That is also possible. I have a small exercise to think of. Can we express the amplitude and the initial phase in terms of x0 and v0? Okay, where x0 and v0 are the initial displacements and the initial velocity. So the question is basically that so we said that the frequency is independent of the initial conditions. Now, is it true for amplitude and the initial phase? The answer is no. Amplitude and initial phase, they depend very much on the initial conditions. And if you look that x is equal to a cos omega t plus alpha, then x0 is nothing but a cos alpha, and v is equal to minus a omega sin omega t plus alpha. So v0 will be minus a omega sin alpha. Then just by doing this squaring and adding appropriately, just finally using the formula that cos squared alpha plus sin squared alpha is equal to 1, you will have a is equal to root over x0 square plus v0 square by omega square, and tan alpha will then be is equal to minus v0 by omega x0. So omega is the source property, but other than that the initial phase is nothing but v0 by x0, and a is nothing but root over x0 square plus v0 plus by omega square. So again, omega square is determined by the source, but other than that I have the initial conditions. So remember, if the source is given, only by knowing the initial conditions I can immediately tell what will be the amplitude and the phase, initial phase of the oscillation in terms of the initial displacement and the initial velocity. So you remember, you see that if the initial velocity is 0, it immediately tells you that tan alpha will be 0 and alpha will be 0. So you will have 0 initial phase. And all of these are possible only because we are working with this specific solution of cosine omega t plus alpha. If this is a sin omega t plus alpha, I suggest you to do the same type of calculation and understand what are then the dependence. Are the dependence same or they are different? Okay, thank you.